we are already 8 minutes past 5. So I think it's a good moment to start an introduction for the Latin American Space Challenge. And then I will present part of our team that is working hard to make the competition happening in November. And then I will pass over to Rafael and Mateus from RocketPy team that are doing a great job developing this tool, this software that is helping not only Brazilian teams, companies, startups, but also European and American rocket teams. And we are glad to have this partnership with them in this year. So, starting a bit, talking about the 2025 Latin American Space Challenge. Yes, we are back after 1 year trying to understand what could be our next steps. We know that 2023, we had a nice moment for many teams, but also we had some difficulties with the weather. Mainly the weather on Saturday was really bad. We had rain, it was really cold, and many teams were not able to launch their rockets on Saturday. Then on Sunday, we had, let's say, 20 rockets to be launched, and our launch window closed by 12. So it was really hard. We know that many teams were not totally happy, but after that, we started to understand what could be done to make possible to all teams launch their rockets. Then in 2025, we are changing things. So the first thing that I would like to say, we are moving from Cape Canaveral to the sugarcane launch range. We are now going to have the competition happening in Bauru and Iacanga. It's a, let's say, a region a bit further from São Paulo. However, it's a nice place. We will have a really, really interesting launch area. I think you guys will like a lot. And the weather is normally better than August. So we are expecting to have good weather and a nice place to have the competition. This is the first part. As soon as we are moving from one place to another place, many authorizations, approvals, certificates are needed to have the event happening. In this way, we are working with our stakeholders, and as soon as possible, we will share the locations, I mean detailed locations. But what I can say is that we are really near Iacanga, is around 10 kilometers to the east from Iacanga. It's gonna be the launch pads. And yes, we are like hoping to have a nice moment with you all in November. The second part of these updates in the competition is that we are working launch slots. So different from the last years, we are not going to work with the first in, first out. Now, every team will have a scheduled launch window. And in this way, we will assure that every team in the tier 1 will have an opportunity to launch their rockets. So this is a good and important movement that was created by the Latin American Space Challenge. And I think that will be adopted by other competitions world around. So around October, we will have the draws for the slots, and it's gonna be a live stream as well. And I hope you guys watch and cheer for your team to get the best slots. Third, we are just near the deadline for the Rocketeers and Satelliteers tickets, team tickets. And what I would like to say to you is that we will not send a reply for emails with proof of payment. Again, we will not send a reply with the for the emails with the proof of payments. We are receiving tons of emails. We are processing every single email, but we will not reply. You can be calm because we know that you paid. We know that everyone is like hustling, going to the Stripe website or paying by Pix and sending the T-shirt sizes, the proof of payments, and etc. But do not expect an answer from us. Okay. Anything that happens, meanwhile, we will talk to you, mainly with your team leaders. Okay. So those were our let's say opening. I'm really happy to have the Latin American Space Challenge happening again. I prefer to say just Space Challenge from now on. So I'm really happy to be part of the Space Challenge. It's going to be our 6th year. So my name is Calvin, and thank you for all Rocketeers and Satelliteers being dedicated all year around to make this happen. So thank you so much. I will now present part of our team is somebody that is really dedicated, and the person that is making the Latin American Space Challenge or just the Space Challenge happening again. So Lucas, please present yourself.
Hey everyone, for those who don't know me, my name is Lucas Miguel. I'm one of the directors of LASC. And as Calvin mentioned, we appreciate and the understanding and patience of all teams. And we are very excited about the 60th edition of LASC or Space Challenge now. And hope you enjoy it too. The only thing I'd like to share with you guys is to stay tuned to LASC's social media for updates. I'd also like to thank the RocketPy team for their partnership and wish you all a great live stream full of learning. Thank you, everyone.
All right. Thank you, Lucas. Thank you, Calvin. It's lovely to be here, and it will be great to be at LASC this year. Let's get it started. So today, what we're going to do is a basic training. We will go over some basics of how to use RocketPy and what you can get from it. We'll also go over what RocketPy will be doing at the competition and why you should give us your simulation. So to start, let me present myself. I am Matheus Stano. I am currently doing a master's degree in mechatronics and robotics in Munich. And I am the current lead of the library development team in RocketPy. So I am responsible for developing basically all the features and make sure the code doesn't break. So if you find any bugs, it's my fault. And I'm here with my colleague, Rafael.
Hello, everyone. My name is Rafael. I am a mechanical engineer, and I am currently the head of public relations and outreach at RocketPy team. So I'm the guy who will ask you to follow us on Instagram and subscribe to our YouTube channel. So please make sure you take your time to do that. You will make me very happy once you follow us on Instagram and tag us and support us through our social media. Before we go to the lecture itself, we're going to present a little bit of RocketPy here for those who haven't had the chance to know about the software, or for those who have this moment as the first contact with the software. So starting with a very simple yet very important question, what is RocketPy? So as it is written in this slide, RocketPy is the next generation trajectory simulation solution for high-powered rocketry. It's a little bit of a tongue twister, but that means that RocketPy is an open source software which is completely developed using Python. It is a Brazilian technology. It was created here, but now the team behind the software is global. We have members in India, Portugal, United States, and so on and so forth. It was made for Rocketeers by Rocketeers. So naturally, the majority of people involved in creating and maintaining the software are members or former members of rocketry teams. But I really wanted to make it clear here that RocketPy does not represent any team. We are not part of any team. We do not compete. We do not have rockets. So please keep that in mind because that is very important and it is related to what we actually do. What we do, it's RocketPy is we are able to provide flight dynamics and trajectory simulations with precision and accuracy, including 6 degrees of freedom and Monte Carlo analysis, that is in this slide. We have a strong integration method, and we take into account the variable mass effects. The user is also able to set a custom atmospheric conditions and have the results very, very fast, which make us the perfect match for rocketry competitions. The next slide, please. As everybody mentioned here today, this will be our first time here at the Latin American Space Challenge or just Space Challenge. But for the last couple of years, RocketPy has been the official simulator for the European Rocketry Challenge, which is the EROC, that takes place annually at Portugal. So even though it's our first time partnering with LASC, we do have experience work in student competitions. And throughout those years, we were able to help the organization with the safety precisions and with the recovery of the rockets. And we are very happy with the relation that we built with Iraq. And we are very thrilled to have the opportunity to work with LASC this year and to build this relation as well here with all of you guys. So talking about RocketPy LASC, we have 3 moments about our participation at LASC that we have to mention here. The first one is this very exact moment. You guys are preparing to submit the second progress report, and you have to submit a simulation of your rockets using RocketPy. That's probably why you guys are here, to learn how to do that. At the competition, that means the on-site operation part of it, we have to run a simulation to make sure that all the safety requirements are met in order to make the launch possible. And last but not least, we have, for the first time ever, the RocketPy Award. So make sure to meet all the criteria necessary to make your team able to compete for this very special award. So without further ado, let's go to the lecture itself.
Yes. Okay. So for the training, we will basically try to achieve these 3 goals. We will learn how to use RocketPy, which will consist of basically how to build a notebook and run the code that will run the simulation. And we will also learn a bit about what to do with the outputs and how to make sure that your simulation is good. Okay. Before moving forward, if you have any questions, you can leave them at chat. At the end of the stream, I guess, we will go over all the messages, and then if there are any questions, we will be answering them. All right? And yes, we will record the live stream will be available after it's done. Okay. So the first thing we should understand about RocketPy is a bit of its structure. So RocketPy is a Python package, which will consist of classes. We don't need to go too much into code. You don't even need to know too much code to be able to use RocketPy. It's actually a great way to start learning code, and especially Python. But basically what we have in RocketPy is these packages right here. And what we will be doing is building each one of these. So first we start with the motor, then we get this motor and we add it to a rocket, okay? Then parallel to that, we build an environment, which is what models our atmosphere. And then with all of that, we create a flight simulation, which will then give us all the results of the flight of our rocket. Okay? A few things that I wanted to go over. for the sake of completion here, is the things that RocketPy don't do. So basically our restrictions as a software. And these are, and I'll go over very quickly. I don't need to be too specific, but I just wanted to have this on record. We do not do rigid or axisymmetric single body rocket, so there's no structural flex or aeroelasticity in the simulation. We have quasi-steady aerodynamics. This means we don't have any aero memory effects, which are quite advanced aerodynamic model, so we have a simpler one. In terms of environment, we have wind that varies with altitude only, okay? We use a local level frame, which is also known as a flat Earth. However, we do consider the Earth's rotation, so the Coriolis effect is considered. We have a varying gravity model that considers an ellipsoidal Earth. Yes. For the aerodynamics, we do have static aerodynamic coefficients, which are functions of Mach and angle of attack. If you need more precision than that, you can define them custom, all of the aerodynamic coefficients of your rocket. And then in this sense, we also do not simulate dynamic stall unless you provide your own coefficients that do simulate the stall effects. And then for recovery, we do not simulate cloth dynamics or line stretch. So basically, once we have the parachute deployed, we have a 3DOF, 3 degrees of freedom model. So we are not simulating the wiggle of the rocket under the parachute, okay? These simplifications are still very, very good. Still we yield good results for our class of rockets, okay? And then moving on, we can actually get started with things. The first thing I want to emphasize is how important our documentation page is. So if you plan on simulating RocketPy, you should go to docs.rocketpy.org. Everything I will talk about here is there also, and in more detail. And also there's much more there. Everything that you need will be there. And if it's not, you should tell us, maybe via our Discord, or maybe right now at the live stream, or anywhere you can contact us, because it should be there. Our idea is that the documentation should have everything. So right now, what we're gonna go through is basically if you went to this page and then you clicked on the getting started there, right here, and then that's what I'm gonna go through here, okay? So there are basically two methods of running RocketPy. One of them is on a local Python, so you can have Python installed in your computer and then use this to simulate with RocketPy. RocketPy is just a package, so it says if you install NumPy or SciPy or any of the basic packages, all you do is a pip install RocketPy and then you have it working. Or alternatively, if you want maybe to share your simulation with a lot of people or the entire team that you have, you can use Google Colab. Google Colab has some interactions with Google Drive as well, so you can share files easily in there. You can find the Google Colab example in the first simulation page. So if you go into the docs, there will be right there first simulation, and then you click there, there's a Google Colab link. There's also the link here on live stream. You can send it on the chat later. And then you have a sample Colab, Google Colab website with the simulation already working. Okay, what's good about this, the Colab, is that it comes in a notebook format, and this is how we actually recommend you to use RocketPy. It's by using these interactive notebooks, also known as Jupyter notebooks or this .ipynb formats. And they are very, very useful for RocketPy because, just like I said, we run the RocketPy in little packages. So we run the motor and then the rocket and then the environment. And what the notebook allows us to do is to run each section of the code individually, and then we can see the outputs of each part individually, and then we can make sure we didn't do anything wrong or the results are good, and then you can already get the information step by step instead of everything in a batch. Okay, so one thing that I want to talk about is a bit about importing files, because we will do this a lot. There will be a lot of files that you need to import throughout the simulation. It's very simple. All you need to do is provide the path to the file in the Python code, or in case you are using Google Colab, You can also include the files in the Colab file, and then you will have them saved locally on Colab. So not locally, but on Colab. And then you can refer to those files directly. This is useful because Colab also can mount to Google Drive. So what you can do, if you want, if your team uses Google Drive, and that's very useful, is to have all your data on Google Drive, and then via Google Colab, you access Google Drive. You can mount your Google Drive, and then you can have direct access to all the files in your Google Drive in Google Colab and your RocketPy simulation. So that is very useful. Okay, so getting started with the proper simulation, we start by setting up an environment, which is basically the model for the atmosphere that we will be using during the simulation. First, basically, what we require is the position of where you want to launch a rocket. So latitude, longitude, elevation of the point of launch of the rocket. And then you will need to set and choose an atmospheric model. And then we'll go into this right now. What are the atmospheric models that we provide? This is where we will define exactly what types of wind and pressure profiles you will have and your rocket will experience throughout its flight, okay? So by default, once you create an environment and you don't add any new atmospheric model, you'll be using the international standard atmosphere, okay? So that is an atmosphere that has no wind and that has some simplified pressure per height profiles. However, another simplified method here is that you can set a custom atmospheric model. And in this way, you can set custom wind values. So you can see here on the example that he's setting this wind U and wind V. So these are wind from south to north and wind from west to east to some specific values. So he's saying that at 0 meters altitude, the wind is 5 meters per second, and at 1,000, the wind is 10 meters per second. Then RocketPy handles the interpolation between these values, so this will basically be a straight line here. And this custom atmosphere model can be very useful if you want to say, check how your rocket flies at a certain very high wind speed. And then you just set a constant speed and then you test it. Or you can have it set any custom things that you want. However, I think more interestingly is the forecast models that we have, so that we can actually get data from data sets that provides weather and atmospheric forecasts to us, and that are quite advanced and will give us pretty accurate results. So what we recommend you doing on a LASC, that we know from experience that is good, is using this windy type, okay? So essentially doing exactly what the code shows here. And then you have 3 options for forecasts, which are from the ECMWF model, the GFS, or the ICON. They're basically equivalent, though they give different answers. If I were to choose one, I would choose the ECMWF, but they are essentially equivalent. One thing that is important to know is that this is a forecast, so the furthest away you are from the day you are simulating, the less accurate the wind results will be. So as it gets closer to the launch day, the values of wind that you'll be using in the simulation will be more and more accurate. This is important because when we are there at LASC, we will be simulating your rocket until the very last second, right before you launch. So we will be having the best possible wind predictions we can to find where your rocket falls on the ground. But yes. Another interesting thing that RocketPy can do is use reanalysis data sets. That is to say, you can get a data set of pre-registered data to see what the wind values were like in past dates. This is very useful for post-launch analysis. So what you can do is you launch your rocket, now you want to re-simulate to maybe compare with the data you have from telemetry, or maybe you have missing telemetry data and you want to complete with simulation values. The best thing you can do is use this reanalysis. Okay, so this allows you to see past weather conditions. And what we recommend you doing is that to get this reanalysis data, you need to access this data set, which is called ERA5. To search it on the web, you'll find it's pretty simple. Okay. Further on, what we have is this ensemble method. Ensemble forecasts are very useful because they are generated by running a model multiple times with slightly different initial conditions. That means that the ensemble forecast is actually, say, 20 different forecasts, all varying slightly, and then they get the average of this, and then theoretically, this is more precise than just a normal forecast. This is extremely useful if you plan on running Monte Carlo simulations. You should use an ensemble. Just a minute. I think the presentation stopped for some reason. Okay, I have to share it again. Just a minute. Okay, should be good. Get back. Okay, so back here, ensemble. Yes, so the ensemble is very useful for Monte Carlo simulations because you give different wind conditions, and then you can use all of this for your Monte Carlo, but then let's move on. So after you run the environment, and you can find this in the Getting Started notebook, you see that there are a bunch of information, and including some plots. The plots will show you the wind profiles and the wind directions throughout the height, and as well as the pressure profile and density of the air, and more things. Moving on. Next thing we do is create a motor. RocketPy can simulate 3 different types of motor. These are solid, hybrids, and liquids. Each of them have their particular inputs that they need. But in general, what we will always need is a thrust curve, which is thrust versus time. We will also need propellant-related information. So for solid motor, this is our grains. For liquid motors, this will be tanks and the fluids that are in them. For hybrids, it will be both things. And then we also need some motor physical parameters, which are mass and inertia and the position of the motor in relation to the rocket. Okay. So moving on to the solid motor. The solid motor is the simplest thing we have to define pretty much. First thing we need to do is define the thrust source right here. The thrust source should come from a CSV file or a .eng file. Okay, to provide these files, you just need to put the directions right here as a string. RocketPy will handle the processing of the points there. So either a CSV or a .eng works fine. And then the other things you provide are grain details. So you have the numbers, the density, the initial inner radius of the grain, so on and so forth. These are basically just the geometry of the grain that we need to know. And then also an important parameter is the burn time. So this is for how long your motor will be burning. If, say, for example, you want to simulate for some reason your motor burning for only 2 seconds, even though your curve here goes up to 4, you can try that. RocketPy will handle it and will simulate your curve for less time than you provided. And yes, this is very important for us, the grain numbers, because with this we calculate the movement of the center of mass of your rocket throughout the flight. And this is very important for the dynamic of a rocket flying. Okay. Then there are some parameters here that have the last name position right here. These position parameters, they need special care because they are positions. The positions usually are relative to a coordinate system. And then we need to talk about what exactly these positions are doing. and what they are relative to. So ideally, what we did was that you can define your coordinate system. That means that as long as all the values you input as positions are coherent with a certain system origin, everything should work. So basically, if you check out the image on the left here, we are assuming that there's a origin of a coordinate system here, so not inside the motor, and then basically we just have to give all of the positions relative to this point, and that's it. If, say, you want the origin to be at the nozzle, all you have to do is set the nozzle position to 0, and then all other distances are relative to the nozzle. That's it. One important thing is that the inertia values of your motor have to be relative to this origin as well, okay? This is very important. Moving on. Now, we have to have special care with hybrids and liquids, because for those types of motors, we have tanks. And tanks need special care for sure. In RocketPy, we have 4 ways to define a tank. All tanks are essentially identical for the simulation. So basically, during flight, they will behave the same, given the same equivalent inputs. All that changes between these tank types are how you will define them. So we have a mass flow rate based tank. That means that to define them, that means that to define it, you will need to provide us with the mass flow rate per time curves. For the mass-based tanks, the same thing. But instead of mass flow rate, we will provide us with mass per time, and so on and so forth. We'll talk about it in more detail soon. Okay. So, for creating a tank, the first thing we need to do is create a fluid. And this is very simple. We simply have to provide the density. And it's very nice to provide the name, so the plots can be better described, so you can know exactly which fluid is doing what when we see all of the plots that we have. And then we have to define a tank geometry, so there's a bunch that we can do. Especially, you probably need a cylindrical tank, I would imagine. So here's an example of how to define a cylindrical tank. And then finally, we got to define the tanks. So like I said, each tank will have different inputs, and important to say, liquids and hybrids can have multiple tanks. So you can have a pressurizing tank, and then a propellant tank, and an oxidizer tank, and so on and so forth. And all the tanks can be of different types. Okay. So like I said, the mass flow rate based tank requires a liquid and gas in and out mass flow rate per time curve. The mass-based tank, we need a mass per time curve. The ullage-based tank, we need an ullage per time curve. And the level-based tank, we basically need the liquid height per time curve. You can choose whichever one you think it's easier to get the data to define them. Okay, so here's an example. In this case, we're creating a mass flow rate-based tank. Okay, so you can see here that we provide the cylindrical geometry, so the tank geometry that we created. We also provide the fluids, so we provide the liquid fluid, the gas vapor fluid that we created. And then down here we provide with the curves, like I said. So we have the flow rate out curves. In this case, we have 0 flow rate in, so there's nothing coming into this tank. And then one very, very important thing is that the initial liquid mass and the initial gas mass needs to be coherent with the curves you provided. So, for example, you're providing a curve that gives us the information of how much mass flows out of your motor per time. So you need to make sure that the initial mass of liquid in the motor is equivalent to the amount of liquid that is flowing out given from your curve. If this is not coherent, the simulation will break and RocketPy will raise an error. Okay, so it's very important that the initial mass is coherent with the curves. Okay, another important thing is the flux time. You should always make sure that the flux time of your tanks make sense with the burn time of your motor. Okay, because the flux time is basically how long we will consider that this tank is flowing. okay, that the liquids are flowing through the tank. Okay. Moving on, we can go into the hybrid motor now. So the hybrid motor is essentially the solid motor, but with an added line where we add the tank down here. So basically do the hybrid motor dot add tank, and then you add the tank. One important parameter here is the position. I'll talk about it very soon. I just want to before show the liquid motor, which is simpler than both of hybrid and solid because they don't need grain parameters. You only need the thrust source, some of the physical data, and then the tanks. Okay. In this case, the liquid motor has 3 tanks, so we just add 3 different tanks. Now, adding tanks require a position as well. The position here is the same logic as the other position parameters. So all you have to do is you define a coordinate origin, give all the positions relative to that, and that's it. If you do this, it will be correct. Okay. Moving on, again, you can then check the outputs of your motor, so you will be able to see the plots of how RocketPy is interpreting your thrust curve. Okay, so this is probably a liquid motor, this is probably something else, maybe a hybrid curve. And then you also find some numerical values. Okay, after you have your motor, you can go on and start defining your rocket property. Now the rocket's initially very simple. All you have to do is give some physical parameters. So radius, mass, inertia, the center of mass position. So I'll talk about the positions as well again, but it's just like the motor, you define your own coordinate system. I'll talk about it soon. A couple of inputs here that are very important are the drag curves. So these are curves per Mach number. Okay. And these are very important for us. This can be a little hard to acquire, so you can get this from CFD simulations. Or alternative, what we recommend you doing is getting from the RASA Aero simulator. So it's another rocket simulator. It has very accurate aerodynamic calculation. So it gives you very, very accurate power off drag and power on drag coefficients. It's very useful to use RASA Aero. Or you can also use OpenRocket. You also provide you with some of these values, okay? Yes, so creating the rocket, then you can set your rail buttons. Again, you give the position of the both rail buttons. And then you add the motor. Perfect, perfect. Okay, so let's talk about these positions again. It's just like the motor. Here you can define a coordinate system orientation. So let's say if you want to consider that a positive value is towards the tail, then you have to use the coordinate system orientation, nose to tail. If you want to do it otherwise, you want the positive to be towards the nose tip, and all you do is tail to nose. That's it. Perfect. Further on, it's exactly like the motor. You can choose the origin of your coordinate system. I think one very useful one that people will want to use a lot is the one at the tip of the nose cone, and this is perfectly fine. All you have to do is when you are setting the nose cone on your rocket, you just put its position to 0, and that's it. Then your coordinate system will have the 0 on the nose cone, and as long as you put all other values relative to this, and as long as they make sense, RocketPy will correctly simulate everything. Yes. Another thing you have to add besides the rail buttons and besides the motor are the aerodynamic surfaces. What you'll be adding probably is nose cones, fins, and maybe a tail. This is all you need probably. For nose cones, we have several different types. Recommend checking the documentation for them, but probably whatever type you need, we do have it implemented. For fins as well, we have trapezoidal, we have ellipsoidal fins, we have freeform fins, so you can define whatever shape you want, and you give them their parameters. And for the tail as well. One important thing, and this is, I can't stress this enough, is that whenever you add the aerodynamic surface, you should always check the rocket draw. Once you check the rocket draw, you'll be able to see if all the positions make sense, and if the rocket you have built, the data you have provided RocketPy actually makes sense. So if your drawing is pretty like this, then all good. If your drawing is not pretty, then you should probably reassess the values that you have provided. Okay. Another important thing to check is always the static margin. Because the static margin will basically define if your rocket can be actually simulated or not. If your static margin is negative, RocketPy will not be able to simulate your rocket. You'll basically run indefinitely. If your RocketPy, if your static margin is higher than 0, RocketPy will probably simulate your rocket. However, it is important that you note the aerodynamic stability recommendations. So it's always good to have static margin higher than 1, okay? And especially for our rocket proportion, so up to 3 kilometers, this is probably the best to have higher than 1. And then ideally, you'd have actually static margins higher than 2 and probably lower than 3. Maybe that'll be the perfect range. This is very important for safety. If you have a static margin lower than 1, you probably have to redesign your rocket to have maybe bigger fins, okay? This is very important. Then finally, you can add parachutes to your rocket. This is very important. For the parachutes, very simple. All you need to provide is the CDS. So this is the drag coefficient of the parachute times its area, okay? You can have multiple parachutes in the same rocket. The other thing you have to provide us is the trigger for this parachute. So say you have a trigger set to apogee, as it is here. This means RocketPy will open your parachute at apogee, will deploy your parachute at whenever apogee is detected, okay? Alternatively, you can, instead of putting the string apogee, just put a number here. This number will mean that whenever your rocket falls to this altitude, you will deploy the parachute. RocketPy will detect this and deploy the parachute in the simulation. The other parameters here are relating to a bit of electronic simulation. So you can simulate the sampling rate of, say, your electronics on the rocket, which would be actually detecting the trigger of the parachute. So for example, you can put a sampling rate of 100. The lag here is also very interesting. So this would be to simulate the lag of your deployment system on your actual rocket. So say it takes 1 second for your system, your deployment system, to detect that you reached the apogee and that you want to deploy the parachute, then you put here on lag 1. This means that RocketPy will detect the apogee and then 1 second later deploy the parachute. Yes, and then if you still want a more complex trigger function here, you can have custom ones. So you can define basically whichever trigger function you want. You just have to check the documentation here and do it properly, but it's not very difficult and it's a very useful thing to do. Perfect. If you have a rocket with variable diameter, RocketPy can simulate that as well. And what you should do is for the transitions, so for the areas where the diameter are changing, you should use a tail. So just like I did here, you can see that this tail has a top radius of 0.6 and a bottom radius of 0.8. So this tail right here is actually the drawing right here. It's going from a smaller radius to a bigger one. And then you add another tail that goes back into the original diameter, and there you go. Things will be calculated correctly, okay? Yes, then at the end, you can also get all of the data from your rocket. So you will, in the all info function, you will summarize everything that we have calculated from your inputs and just put it out there. So you can check if everything is coherent and everything makes sense to your actual physical rocket. And then finally, once you have the rocket and the motor and the environment, you can create a flight object, which is what actually will run your simulation. So basically, the extra numbers you have to define here are rail parameters. So the inclination of a rail relative to the ground. So if it's 90 degrees, then the radio would be pointing straight up. Usually we'll set to 85 or something about the range. So it is a little bit inclined. Then you can set the heading. So a heading of 0 is pointing north. If you have put a heading of 90 degrees, then it's pointing east, so on and so forth. And then obviously the rail length, which is the length of a rail. And And then yes, once you run this, you have the simulation, and then you can run the info and now info functions to check all of the data. And in here, you have everything you always need. What is very important for you to check is always the rail departure velocity. I believe in LASC rules, there was probably a minimum velocity here that you need to have. So this is very, very important that you check that this is actually the minimum. You definitely want to see the altitude, the apogee. All right, so it gives you the apogee values. It gives you both ASL and AGL, that is above sea level and above ground level. You probably want to know the above ground level, which is the one the competition will be caring about, okay? And yes, and then you have everything else. So for example, the impact points, you have the latitude and longitude. This will be very important, obviously. But there's a cooler way to see the impact points. I'm going to move forward a bit, which is to actually export the trajectory to Google Earth, as I explain it right here. So with this little function right here, you export to a KML file, which is a file that if you open, will open Google Earth on your computer. And on Google Earth, you'll be able to see the trajectory of your rocket and obviously the impact point. And this is super, super cool. You can actually automate this so that whenever you run the simulation, you already create a Google Earth and then you just check it on Google Earth as soon as your simulation is run. We will be having this on LASC on site. So right before you launch, if you want to see the trajectory of your rocket, you can go to us during the competition and we'll probably have something like this showing up on our screens, okay? Let me just go back here because I want to talk about some of the plots here. So obviously we have plots of pretty much everything the rocket will simulate. And then obviously you can also get the data and do your own plots and do whatever you want with the simulation data. One plot that I want to talk about that is very important is the stability margin. So before I talked about the static margin, how important it is that it is above 0, especially. The stability margin is even more important because this one actually profiles your stability throughout the flight. So with all the variations that the flight profile provides to your rocket. So this stability margin is the plot you actually want to see to guarantee that your rocket will be actually stable, okay? If you have a solid motor rocket, this will probably be fine if your static margin is okay. But if you have a hybrid or a liquid, this can be a little tricky. So your stability margin will probably be a little different than your static margin curve. So it's very important that you check this and make sure that these numbers are good. Okay. Yes, like I said, you can export all the data you want to CSVs or to JSONs. If you want something like this, export it to KML, and yes. And going further than just one simulation, you can do many, many more advanced things with RocketPy. One of the most useful things that I recommend everyone does is the Monte Carlo simulation. So this is basically, you basically take your simulation of a rocket, you set a bunch of standard deviations to the parameters. So you have a bunch of random rockets, and then you simulate, say, thousands of flights. And then with this thousands of flights of your rocket in thousands of different states that are a little different. So you have thousands of rockets that are different from each other in very small ways. That will be based on some statistics, right? Some standard deviation. Then with these thousands of simulation, you can get a very good prediction of where your rocket will actually land. And this is super, super useful, and this works very, very well. So I highly recommend that you look into the Monte Carlo. The things you can do is after the Monte Carlo, you can do sensitivity analysis. So that is, you'll be able to see what parameters of a rocket affect the most your trajectory. Or you can do multivariate rejection sampling, or MRS, which is basically you have a gigantic Monte Carlo simulation and you want to change one parameter. So this, instead of rerunning the thousands of simulations, you would just get a sample, a smaller sample of this Monte Carlo that already has that new sample value. It's super, super interesting. You can also simulate sensors in your rocket if you want. So you can add an accelerometer to your rocket in RocketPy, and then you simulate the discretization and the range of values of an accelerometer. So if you have some controller logic or maybe something in your payload that you want to simulate, you can use this. We have accelerometers, we have gyroscopes, barometers, and GNSS sensors. So you can do all of that. You can perform some control simulations. So we do have a controller capability. It's a little limited right now. So one thing that we support 100% is air brakes, but we don't support, for example, thrust vector control yet. And also controlled recovery would be a little difficult to do right now, but we're getting there. In the future, we will have all of those features in the code. And then as well, what you can do is define custom aerodynamic coefficients. I think I talked a bit about this already, but if you have a very complex CFD analysis or something, a weird shape in your rocket for some reason, maybe a camera or something, and you want to customize the aerodynamics a little bit, you can do this. It's all there. And then talking a little bit about some utilities here, is that basically everything I talked about here is on the documentation. You can find it there, and it will be in more detail. So I highly recommend that you check the documentation. In there, you should find everything you need. One thing that is very, very useful, though, is that we have some real flight examples with simulations from other teams, and sometimes when they provide us, the comparison with the data from their actual flight. And we have a page in the documentation that is full of these examples, and these are very useful because you can just check an example of, say, a hybrid motor rocket, and then just follow exactly how that team did it. Or you find an example of, I don't know, any types of rocket, and then just follow the example of exactly how the team did it, just change the values to your rocket, and then you have a working simulation, okay? We also have a documentation here of how to do deployable in case you have any deployables in your rocket, deployable payload or whatever. And of course, the air brakes is also there explained in detail. Then, for the last thing, I want to talk about the OpenRocket conversion to RocketPy. I know many of you already know how to use OpenRocket. So, what we can do is convert the OpenRocket file you have to RocketPy very easily. We will basically generate a notebook with all of the code that runs RocketPy based on your OpenRocket simulation. It's very easy to do. So we have this, it's called the Rocket Serializer. So if you search on Google, you should find the GitHub repository. And then if you scroll down a bit, you have the tutorial exactly of what you need to do. It's very, very simple. I'll go over it here. Basically, what you have to do is have Python installed in your computer. Then you have to install this Rocket Serializer with pip install Rocket Serializer. If you've used any Python packaging, you know how this works. It's very simple. Then you need to have a working OpenRocket, which you probably need to have a working OpenRocket. You already need Java. So these two things are a requirement, okay? Then all you need to do is go into a command prompt. In the command prompt, you will write this command right here. So ORK, or OpenRocket to notebook, okay? -- file path, and then the path to your OpenRocket file. And then this should already generate a notebook for you that you can open. You have all the RocketPy codes, okay? There are some limitations with this. You have to save your OpenRocket file in English. That's very important that you do. We are not taking into account all the languages that OpenRocket supports because it has a lot. You do have to have the rocket simulated in OpenRocket, so you have to go through all of the OpenRocket process. You can just define the geometry. You have to define the geometry and run the simulation, okay, on OpenRocket. And then we can apply the conversion. We only support one stage rocket, so only one motor and only one nose cone, okay? Then with all of that, you should be able to convert your OpenRocket to RocketPy very, very easily. Perfect. And then that's it, I think. If you have any questions, you can send them on chat, but thank you very much for your attention. Let me check the questions here. Interesting to add a feature to add antenna point and antenna coverage. That is nice. That is actually nice. One thing you can do, Lucas, to make sure that we don't forget this is, let me get a link here. GitHub on our GitHub page, we have an issues page where you can write suggestions for features. I'll send you a link here on chat. And then if you write that on the issues, then we will never forget your suggestion, and eventually we will implement it. So I'll send you the link. Issues, okay. One thing we will do is that we will put the live stream will be saved on YouTube, and then on the description here we should probably put all the links that show up during the presentation, so that you can easily access the documentation that was mentioned during the presentation. Okay. Yeah. Thank you very much, guys. I think there are no questions.
Mateus, Rafael, thank you so much. Lucas, thank you. Thank you all, guys, for participating in this RocketPy training. And as the event director of Latin American Space Challenge, I have to say that I used in the past the RocketPy for real launches with the Brazilian Air Force. And RocketPy is a software that I trust. I had the opportunity to recover. I was talking to them before the live stream going on, that our team had the opportunity to recover the black box of our rocket in the middle of the ocean, based only in the RocketPy Monte Carlo simulation. So it's a great feature and software that has been being developed by the RocketPy team. And in this partnership for 2025, we are expecting to have better simulations and easier recovery of our rockets. So then, thank you so much, Mateus and Rafael and our RocketPy team to partnershiping with us, and we look forward to this during the event. I hope you guys will be there, supporting all the teams running their simulation as well. Thank you so much.
Yes, thank you, Calvin.